Welcome, everyone. For this lesson, we're going to be looking at the alternating series test. And we're going to see how we can use this test to tell us when an alternating series is convergent. And the helpful thing about this test is this one allows for a series that has negative terms. It has to be in a specific order, positive alternating between positive and negative, but it allows for negative terms. So all of the series tests that we've looked at so far, comparison, limit comparison, integral test, those major ones, everything had to be positive. But now we're kind of getting into the realm where we're allowing some negatives. So first, let's look at the statement of the test. So the alternating series test here. So given an alternating series of the form sigma n equals 1 to infinity, negative 1 raised to the power n minus 1 times bn. Now the idea here is this power of negative 1, this is what makes it alternating. This is kind of the alternating piece here. So this is something we've looked at before. These powers of negative 1 just bounce back and forth between positive and negative 1. And the idea is we kind of separate off that alternating piece. When we write our alternating series, we kind of want to separate off that power of negative 1 and then look at kind of all the other stuff. And all that other stuff, that has to be positive. So we want to separate off everything else. So when we have a series like this where we see a power of negative 1, we're going to move that power of negative 1 to the front and then still inside the sigma here, but then we'll kind of have everything else grouped together. And we're going to be looking at all this other stuff. Really where what happens is it depends on that bn. And so there's some things we need to check in order to use this alternating series test. We have to show that bn plus 1 is less than or equal to bn for all n. And the limit of bn is equal to 0. So there's kind of two things we want to check here. And actually, usually, it's better to show the limit of bn to be 0 first. So we're going to usually do that one first. So we want to show that the limit is equal to 0. And then we want to prove the inequality. And this inequality shows that we have a decreasing sequence. So what this says is that bn is bigger than its next term, bn plus 1. So the terms are decreasing. So we can prove this a few ways. We could prove this using derivatives or kind of more of just a direct proof using inequalities. All right, so if we have an alternating series like this, where the non-alternating part here is all positive, and we prove that the limit is equal to 0 for that non-alternating part, and that non-alternating part is a decreasing we prove this decreasing inequality, well, then the alternating series converges. Okay. So, and just a little example of what these things look like. So if we write out the first few terms for this alternating series, well, when n is equal to 1, we'd get b1. And then when n is equal to 2, we're going to get b2. But then 2 minus 1 for that power of negative 1 is going to give us negative. And so we end up with this positive, negative, alternating between positive and negative values. So an example is, or a few examples here, these show up a lot of places. Sum from n equals 1 to infinity, negative 1 raised to the power n. And over n. And what we see here is we start negative, then we get positive, then negative, then positive. So we have that alternating piece. Now it's not quite written as how we wrote it in the actual test here, and that's okay. So this test works if that alternating piece, that -1 raised to the n minus 1, we can replace that with similar terms. So probably some of the more common are -1 raised to the power n, or -1 raised to the n plus 1. Those are probably the more common ones here. And just like with all of our other tests, the conditions don't have to be satisfied right away, as long as they're eventually satisfied. So, if we kind of go back up, and really the only one, well, there's kind of two here. Bn is positive. It's okay if the first few terms aren't, this doesn't necessarily work out, as long as we reach a point where from then on, all of the terms, Bn terms, are positive. And same thing with the decreasing inequality here. It's okay if there's a few terms at the beginning where we kind of go up, where we increase, as long as we do hit a point where then from then on, our terms do decrease. Okay. And again, just a warning here. The comparison tests and the integral tests can't be used for alternating series, because for these two tests, or these three tests that we've looked at, all the terms had to be positive. Couldn't have negatives. Okay. So let's try example 1. We want to figure out if this series, sigma n equals 1 to infinity of -1 raised to the n over n, is convergent or divergent. And so a lot of times it's helpful, not necessary, but helpful, to kind of separate off the alternating piece. So let's take that -1 raised to the n and just kind of separate it off. So we have the alternating piece here. That's what gives us the bouncing back and forth. And then we have all this other stuff, 1 over n in this case. So we have the alternating part, and then we have this 1 over n. All right, so for this alternating series test, first thing is we just want to state what Bn is. So in our case, it's all the stuff without that alternating. So Bn is going to be 1 over n. So you just want to have a nice clear picture of what we're going to be working with. Then, and we can check, this is always positive when n is greater than or equal to 1. Okay. So then after that, we want to calculate the limit. So we want to do the limit of Bn. Again, for the alternating series test, we're kind of working with this, the non-alternating part. So we want to calculate the limit of Bn and show that this limit is 0. So we're doing the limit as n goes to infinity. Let's fill in what it is. So in this case, 1 over n. And this is just a c over infinity form. So there's really not too much work here. This definitely does go to 0. So limit equal to 0, check. Okay. What's the next thing we need to show? We next need to show that it's a decreasing, we have a decreasing sequence here. So we need to show that Bn plus 1 is less than or equal to Bn. All right, so let's first write out what it is we want to prove. So let's first figure out what is Bn plus 1. So we know what Bn is. That's just this 1 over n. So, and what this is, you can kind of think of this like a function. What we're doing is we're plugging the number n, and we get 1 over n. So what happens if we plug the number n plus 1 in? Well, we're going to get one over n plus 1. So sometimes it helps just first state, specifically just state what Bn plus 1 is. So all we're doing is we're taking n, plugging it in, we get 1 over n for Bn, and for Bn plus 1, we're just changing that n to an n plus 1. And so the inequality that we want to prove here is that bn plus 1 is less than or equal to bn. So this is what we want to show. So we don't know this yet. So let's actually write out what our two terms are. So bn plus 1 is 1 over n plus 1, and bn is 1 over n. Again, write out what you want to prove. And if we cross multiply here, we end up with n is less than or equal to n plus 1, and that's obviously true. And so because this statement is true, that means this statement was true, which means our inequality is true. All right. And since we got both of those conditions satisfied, now we're ready to state our conclusion. And that is this series, negative 1 raised to the n, from n equals 1 to infinity over n, converges. And whenever we kind of state a conclusion, we want to make sure that we include the name of the test that we used. So the alternating series test here, and abbreviate that AST. All right, so that's really it for the alternating series test. So let's just kind of go back up, make sure we hit everything. So when we use the alternating series test, usually it's helpful, separate off the alternating part, and then look at everything else. And this is really where we do most of our work. Usually it's helpful, show that the limit of that term is 0 first, because as we'll see, if you get that it's not 0, then the test is over with. You can't do any more. And then once you prove that the limit is 0, then you want to show that decreasing inequality. And once you did both of those, well, then you can make your conclusion. The series is convergent. All right, so let's try another one. Let's look at example 2. All right, so first of all, again, usually helpful, let's separate things off. So let's rewrite this just a little bit. I see I have this negative 1 raised to the n plus 1. Let's get that alternating piece out of there. And then we got 2n squared over 5n squared minus 3. Again, you don't necessarily have to do this, but I think it's helpful. All right, so what we have our alternating piece, and then we have bn. So to get our alternating series test going, we just want to start by stating bn. So bn in this case is 2n squared over 5n squared minus 3. Okay. And n here is, we're starting at 1 and going to infinity. So there is some subtraction here in our denominator. 2n squared is always positive, but when n is 1, that 5n squared is already bigger than 3, so we're okay. So all these terms are positive. Okay. So we state bn. Step 2. We want to show that the limit of bn is equal to 0 as n goes to infinity. All right, so let's do this. So we're going to do the limit of 2n squared over 5n squared minus 3 as n goes to infinity. And this is our kind of usual rational function here. And we could do this two ways. We could do, if we think about it, as n gets big, the numerator is going to infinity and the denominator is going to infinity. So we could use L'Hopital's rule, but it's usually easier to use our algebraic technique, where we pick out the largest power of n in the denominator and then just divide every single term by it. So let's do that. So we get 2n squared over n squared divided by 5n squared divided by n squared minus 3 over n squared. And if we clean that up, we end up with the limit n going to infinity. And if we simplify in the numerator, we're going to get a 2, and then a 5, and then minus 3n squared. And this ends up being 2 over 5. So that's no good in terms of our alternating series test. This is false. So we can't go on any further. So the alternating series test doesn't work here. So this is why it's helpful. Show that the limit of Bn is 0 first, because sometimes you might get something where it's not 0, in which case the alternating series test doesn't work. So you don't even want to go on and prove that it's a decreasing sequence. Okay, so what are we going to do instead? So the limit here is not equal to 0. Well, the nice thing about this is if this happens, we can just immediately switch over to a test that we've looked at before, and that is our test for divergence. So when this happens, we can use test for divergence instead. And so what we just showed is that the limit of 2n squared over 5n squared minus 3 as n goes to infinity is equal to 2 over 5, which implies then, if we look at the limit of the entire thing with that alternating piece included now, does not exist. So if we include that alternating piece, so if we find that the limit of something is equal to a non-zero number, well, including that alternating piece means we're kind of bouncing back and forth between some numbers are getting close to 2 over 5, and then some other numbers, the alternating ones, are getting close to negative 2 over 5. So it kind of keeps bouncing back and forth between these two different values. And so the overall limit here does not exist. And so when we remember back, what the test for divergence says is if we calculate the limit of just the terms in our series, and it's not 0 or does not exist, well then automatically divergent. So since the limit of the terms in our original series does not exist, well then the series sigma an diverges by that test for divergence. So this sometimes happens. We're trying to do our alternating series test because we do have an alternating series, but we get that the limit does not equal 0, so the alternating series test doesn't work in that case, but instead we can immediately switch over to this test for divergence. And so this sometimes happens, so it's worth mentioning. So if the limit of Bn does not equal 0 as n goes to infinity, then the limit, if we include that alternating piece in there, does not exist. So if the limit of Bn is equal to some number, well then by throwing that -1 in, that power of -1, we're going to be bouncing back and forth between values that are getting close to the positive version of that number, and then terms of our sequence are getting close to the negative value of that number. So we're kind of bouncing back and forth between two different values. And so the limit does not exist. And so when that's the case, we can immediately use test for divergence instead. Okay, so that's helpful to keep in mind. Let's try one more, though. Let's look at example 3. So we got another alternating series. Again, we see that we have this alternating part, -1 raised to the n minus 1. And then we got all this other stuff, n and n squared plus 3 in the denominator. So I think it's helpful. Just kind of rewrite the series where you just really separate off that alternating piece. So we have n over n squared plus 3. All right, so this is an alternating series. We have that alternating part, and then we have this term n over n squared plus 3. All the terms here are positive. So first step, we just want to state Bn. So Bn in this case is n over n squared plus 3. And all of the terms here are positive. Okay. So then we want to show that our limit of this, as n goes to infinity, is equal to 0. So let's write out what we want to prove. We want to do the limit of n over n squared plus 3 as n goes to infinity. Again, we're just looking at the kind of this non-alternating piece. This is our Bn here. And kind of like what we just did in the previous example, we could pick out the largest power of n in the denominator and just divide every single term by that. So if we do that, we get n over n squared divided by n squared over n squared plus 3 over n squared. N going to infinity. Simplify, we end up with the limit as n goes to infinity, 1 over n, 1 plus 3 over n squared. And these 1 over n and 3 over n squared, these are c over infinity forms, so they both go to 0. So this goes to 0, this goes to 0. And what we end up with when we calculate the limit is, well, just 0 over 1 plus 0, which is just 0. So, checks out. All right, so that first condition satisfied. It's equal to 0. All right, what do we need to do next? This is where we need to prove that inequality, that Bn plus 1 is less than or equal to Bn. All right, so before we do prove the inequality, it's helpful to first write out what is Bn plus 1. So this is Bn, where we have this formula and we've plugged in just n. So what we're going to do is we're going to swap out each of those n's with n plus 1. So we end up with n plus 1 in the numerator divided by n plus 1 squared plus 3 in the denominator. All right, so we want to prove, what's the inequality we want to prove? Well, let's write it out now. So we want to prove that n plus 1 over n plus 1 squared plus 3 is less than or equal to n over n squared plus 3. All right, so how are we going to do this? Well, this is not altogether obvious here because we have our denominator getting bigger, so usually that's an indication that things are going to decrease, but the numerator also gets bigger here. So we're going to prove this by just kind of reducing it down to a point where we have a statement that's obviously true. So the first thing we can do is, because these terms are positive, we can, really cross multiply, and that preserves the inequality. So I'm going to have n plus 1 times the denominator from the other side. So I'm going to multiply the n squared plus 3 on both sides. And then I'm going to multiply both sides by the n plus 1 squared plus 3. Okay. And now, if you're ever getting kind of stuck, still not altogether obvious here, just multiply things out. So let's do that. Let's multiply things out here. So on the left-hand side, let's FOIL this out. And when we do that, we get n cubed plus n squared plus 3n plus 3. Okay. And what about on the right-hand side here? Well, let's first FOIL out that n plus 1 squared. So we're going to get n squared plus 2n plus 1. And we'll have a plus 1 here, but then we also have this plus 3, so that'll be plus 4 if we consolidate that. Now let's distribute. Keep going a little further. And we end up with n cubed plus 2n squared plus 4n. All right, so now let's try to consolidate similar terms. And on both sides, we notice that there's an n cubed. So when we subtract n cubed from both sides, that's going to cancel. And then we have a 2n squared here. So let's subtract n squared from both sides. And then let's subtract 3n from both sides. So once we do that, we end up with 3 over there on the left. Just that constant, that's all by itself. And then we end up with an n squared plus n. And this is not always true. So our series here was starting at n equals 1. So when n is 1, we end up with 1 squared plus 1. 3 is definitely not less than or equal to 2. But once we hit n equals 2, we're okay. So this is true for n greater than or equal to 2. And so as long as it's eventually true, it's okay if there's a few terms towards the beginning where the inequality doesn't work, but it should work once we hit a certain point and from then on. So in this case, it's okay once we hit n equals 2. Then it's true from then on. So because this is true, we can just kind of reverse our steps. This is true, implies the previous line was true, implies the previous line was true, one before that was true, and then the inequality that we wanted to prove is true as well. All right. So that's it. We've done it. We've gotten both conditions satisfied for the non-alternating part of this alternating series. So now we can state our conclusion. The sum of, what was it, -1 raised to the n minus 1 over times n over n squared plus 3 from n equals 1 to infinity is convergent by that alternating series test. All right, so there we go. We got another test under our belt here for us to use. So we've got our test for divergence, we've got our integral test, we've got our direct comparison test, we've got our limit comparison test, and now we've got our alternating series test. So what we're going to see next, well, a few more tests. So we're getting there. We're getting to where we're going to start really using these things. But first, we'll do a few more of these types of tests. So we'll see you then. Bye-bye.